Hello friends, from this lecture we will start second unit of our elementary number theory. Okay, first unit was the theory of digit. Okay, in our textbook this is not the next chapter. Okay, in our book 2 units are combined in one chapter. But as per the syllabus of our university, from this topic, that is theory of prime numbers, they consider it is unit 2. This unit 2, unit 1 and unit 2 are combined in textbook in first chapter. Okay, so don't be confused. From this, the topic prime numbers, we are going to start our second unit of number theory. Okay, so unit second and topic is first topic is prime numbers. Okay, so prime numbers. This is topic from unit 2. Okay, but in book it is continuing in first chapter. Okay, so you may know the concept of prime number, but I will again clear your idea about the what is the prime number, what is the composite number. Okay, first is the number 1, 2, 3, 4, 5, 6. Okay, 7, 8. What are the factors of 1, or which are the proper divisors of 1? Divisors we write here, divisors. So divisor of 1 is only 1. Okay. What are the divisors of 2? There are only 2 divisors. One is 1 and other 2 is 7. Okay. What are the divisors for 3? The divisors for 3 are only 2. One is 1 and other is only 3. Only 2 number divides 3. No other number divides 3. What are the divisors of 4? 1 divides 4, 2 divides 4, 4 also divides 4. There are 3 divisors. Okay. What are the divisors of 5? 1 and 5. What are the divisors of 6? 1 divides 6, 2 divides 6, 3 divides 6, and 6 also divides 6. Okay. And so on. Similarly, what are the divisors of 7? Only 1 and 7. What are the divisors of 8? The divisors of 8 are 1, 2, 4, and 8. Now look at this. We will not go beyond 8. Okay. We will clear your idea about prime numbers from this example. Now look at this. From 2, each number has at least 2 divisors. Here 2, 2, 3, 2, 4, 2, 4. Okay. So after this 1, every number or every integer has at least 2 divisors. Okay. 2 has 2 divisors 1 and 2. 3 has 2 divisors 1 and 3. 4 has 3 divisors 1, 2, 4. 6 has 4 divisors 1, 2, 3, 6. Okay. Now those number has only 2 divisors. One is 1 and other itself. Look at 2. Only has 2 divisors. One is 1 and other 2 itself. Look at 3. One divisor is 1, other 3 is itself. Look at 5. One divisor is 1, other is 5 itself. So look at 7. One divisor is 1, other divisor is 7. Okay. These numbers are called prime numbers. Okay. Number is called prime if it is greater than 1 and has only 2 divisors. One divisor is always fixed 1, 1, 1, 1. Another divisor is itself a number 2, 2, 3, 3, 5, 5, 7, 7. Such numbers are called prime numbers. And the remaining numbers are composite number. Here we are not talking about 1. Okay. The number is said to be composite. If it is greater than 1, it is not prime. Now 4. 4 has 3 divisors. This is 1 and 4 are other divisors. Any number greater than 1 has 2 divisors. Always 2 divisors. One is 1, other itself. These are called improper divisors. And The divisor other than this are called proper divisor. 4 has one proper divisor, 2, and 2 improper divisors. Total divisors are 3, greater than 2. 6 has 4 divisors. 1 and 6 are improper divisor, but 2 and 3 are proper divisor. Okay. So this 6 has 4 divisors greater than 2 divisors. Okay. 8 has 4 divisors greater than 2. So this number 4, 6, 8 has a divisor greater than 2. Either 3 or 4 or more than 4 also. Some numbers maybe go beyond 8. Such numbers are called composite number. Okay. So this is the idea of prime numbers and composite number. So if you want to write definition, a number or integer, we can say integer n. Okay. Integer is said to be prime if two conditions satisfied. One condition is p must be greater than 1. Okay, because prime number start from 2, and second condition is that n has only 2 divisors, and the 2 divisors are the number n itself and other is 1. Okay, then number is said to be prime number. And second definition is composite number. Definition is also very simple. And integer n is said to be composite if n is greater than 1, and second condition is that it must have more than 2 divisors and at least 3 divisors, or second condition is that n is not prime. Okay, or we can say n has greater than 2 divisors or at least 3 divisors. Or we can write a number said to be composite if it is not a prime number. Okay, so understand composite number and prime numbers. Okay. You can see 23 is a prime number because there are no proper divisors to 23. Only 1 and 23 divides 23. But so 23 is prime. But 21 is not prime. Why? Because there are the divisors like 3, 7. These are divisors. 1, 21. These are the improper divisors. But friends, now we will prove that every positive integer greater than 1 has at least one prime divisor. At least one prime divisor. Okay. You can check. Take any integer greater than 1. Say 6. It has two prime divisors. One is 2, other is 3. 2 and 3 are prime divisors of 6. Take 5. 5 is itself a prime divisor of 5. Take any number, say 16. Okay, 2 divides 16. This implies 16 also has a prime divisor. So any positive integer greater than 1 has at least one prime divisor. We have to prove this theorem. Okay. So proof is simple. We will prove this by the method of contradiction. Okay. Suppose we will assume. We will prove this theorem using method of contradiction. Okay. So we have to assume which we have to don't prove. Okay. We have to prove every positive integer greater than 1 has at least one prime divisor. We will assume that there exists a integer m which does not have prime divisor. We are assuming that there is some integer m which don't have prime divisor. We have to prove every positive integer greater than 1 as a prime divisor. So suppose we will prove this theorem by contradiction. So suppose there is integer m greater than 1 which does not have any prime divisor. Okay. Let S be the set containing such integers greater than 1 here we set containing integers greater than 1 having no prime divisor. Okay. This means, and this set is not empty. Okay. Set S is not equal to empty set. Why? Since we have the integer m, we don't have prime divisor. So this m belongs to the set S. Okay. So that the set is not empty. Okay. Now, by well ordering principle, by well ordering principle, this set S have least element say n. What is well ordering principle? Well ordering principle says every set of non-negative integers, that is every set of positive integer, has least element. Okay. So let n be the least smallest element of the set n. Okay. So we have n divides n itself. N divides n. Okay. And n is in set S. So n has no prime divisor. Okay. This implies n does not have prime divisor. Also n divides itself. Since n is in set S, n does not have prime divisor. N itself divides n, and so n is also divisor of n, and n does not have a prime divisor. So n cannot be prime. Okay, this implies n cannot be prime number. And n is greater than 1. N is not prime, means n is composite. This implies n is composite number. N is composite number. This means we can write n as a product of two numbers where a and b are the integers such that a and b are less than n. So a is greater than 1 and less than n. Also b also greater than 1 and less than n. Okay. Now this a is less than n, b also less than n, and n is the least element in the set which don't have prime divisor. Since a is less than n is the smallest element which don't have prime divisor, and a is less than n. This implies a has a prime divisor. Say p. Why? n is the smallest element, or n is the smallest integer which have no prime divisor. So any element or any integer less than n must have prime divisor. n is less than n, so n must have prime divisor. Say p. That is p divides a, where p is a prime. From this equation we can see a divides n. So and a divides n. You know the property of divisibility. P divides a divides n. This implies p divides n. This implies n has prime divisor. But this is contradiction. Why? Because n is element in the set S which don't have a prime divisor, and we are getting n has a prime divisor. So this is contradiction to our assumption. What is our assumption? We assume that there is integer which has no prime divisor, which is not true, which is false. This implies every positive integer greater than 1 has a prime divisor. This implies every positive integer greater than 1 has a prime divisor. Why? Because we get a contradiction. So our assumption is wrong. This implies our assumption is wrong. This implies every positive integer greater than 1 has at least one prime divisor. I will repeat this proof again. Okay. What you have to prove? You have to prove that every prime integer greater than 1, every positive integer greater than 1 has a prime divisor. Okay. We will prove this using method of contradiction. So we are assuming that there is integer which don't have prime divisor. We have to prove every positive integer has a prime divisor. We are assuming reverse. We are assuming that there is an integer which don't have prime divisor. Okay. So let S be the set containing such integer which don't have prime divisor. Now by Wheeler ordering principle, this set must have least element, smallest element, say n, and n is in the set S. S is the set of element which don't have prime divisor. So n don't have prime divisor, and n also divides itself. So n cannot be prime. Why? Because if n is prime, then n divides n. So n have prime divisor, but we are saying n don't have prime divisor. So n cannot be prime. Means n must be a composite number. And since n is composite number, we can write n as a product of a and b, where a and b are less than n. Now a is less than n. N is the smallest integer having no prime divisor. So any element less than n must have prime divisor. A is less than n, so a must have prime divisor. Say p. So p divides a. From this a divides n. So p divides a divides n. So by divisibility, p also divides n. So we are getting that n has a prime divisor, but this is contradiction to our assumption. We are assuming that n don't have prime divisor, and we are getting n have prime divisor. This is contradiction to our assumption. So our assumption is wrong. What is our assumption? That there is integer which don't have prime divisor. This assumption is wrong. So what is true? The true is that every positive integer must have at least one prime divisor. Okay? This is the proof.